Hi, everyone. Excited to be here. My name is Josh Tobin. I'm co-founder of a new, very early stage machine learning infrastructure startup. Um, and before that, my background is in machine learning research. So I was at OpenAI for a while, did my PhD at Berkeley, um, and currently back at Berkeley as a lecturer teaching this class that I kind of introduced well, most of you were on the call earlier, called Full Stack Deep Learning. Um, and what I'm going to talk to you about today, I know that I had an abstract around testing machine learning models. I'm going to do something slightly different. So this, go ahead. Oh, just someone not on mute. So I promise this will still be relevant if you're interested in testing machine learning models. But I thought I would instead of giving like a very informational talk, I thought I would give like something a little bit more provocative. So this is really going to be in three parts. The first part is I'm going to give a little bit of my view about where we're at as a field in machine learning right now. So that's the first part. And then I'm going to talk about the tools, like the tooling and infrastructure landscape that's evolving in the ML world. And I'm going to point out some gaps that I see in that landscape. And then the third section, I'm going to propose an idea for like maybe a concept that we could use to overcome some of those gaps. All right, so starting off, my view of where we're at in the world of machine learning right now. So to summarize it in a sentence, my view is that machine learning is now a product engineering discipline, right? And so what do I mean by that? Well, first of all, I'm not the only person that believes that. Elon Musk agrees with me, so that's my evidence slide. But what do I mean by that, right? So let's think about the history of kind of machine learning as it's applied in industry. So if we go back to the 2000s, like people were already starting to use machine learning in industry, but they were using it in a relatively specific way outside of the Googles of the world, and that was like what I would call machine learning as analytics, right? So you train a simple model, like maybe your regression, and you run it offline on some data, maybe not a ton of data, but like a medium amount of data, and you produce a report, right? And so the value that machine learning generated for your business is comes from how well you can incorporate the insights from that model into the decisions that you're making as a business. Around 10 years ago, we kind of started what I would categorize as a second era of machine learning in industry, which is the hype era, right? And so this is kind of categorized by machine learning startups that didn't have products raising millions and millions of dollars, and people were like training these really complicated models on massive data sets, and every Fortune 500 C-suite person was like, AI is a strategic priority for us without even really knowing what that means. And so I think like I would argue that this wasn't totally irrational, but the value that most companies were getting out of machine learning, over the last 10 years was really from like PR and marketing, more so than like those models actually helping generate value in their businesses. And I think, I hope that what we're beginning now is kind of an era of like machine learning being embedded into products, and where companies like are starting to realize that having a machine learning team like sitting off in a corner that's like making cool reports and producing proofs of concept is doesn't constitute an AI strategy, right? And hopefully that an era where like people start to judge the value of machine learning teams output based on how much business value it generates for their companies. So this is where I think we're going, and I think we're already starting to see this play out. And so one thing I'll point out is that I think for those of us that are working in teams where there's not a tight tie to business value right now, this presents a bit of a problem. The way I would categorize the problem is that building products that have machine learning embedded into them, it's not just like, take your model and put it into production. It actually requires a pretty fundamentally different process and mindset to building kind of research-oriented ML models. And the way I would characterize that is, if you think about the process of building a model in a research setting, you might select a problem to work on, collect some data, clean that data, label it, train a model to solve that task. And there's kind of a loop there, right, where you're iterating on which model is best fit for that data, like which model solves the task best. But then once you find it, the output of that process is a report of some kind, right? So it's a proof of concept, it's a paper, it's a dashboard, something like that. I kind of the jab I like to take at this is like the way I would characterize this is I would call it like flat Earth machine learning, right? And so it's just like flat earthers believe that there's an end to the world and then everything kind of falls off after that. Flat Earth machine learning people believe that when you ship a model, like when you produce the report, that's the end of the Earth, right? Like you're done. You're done once you train that model. But that's not enough to actually get stuff to work in production. And I think the sort of most succinct way to describe what needs to be different is that there's in the model training process, right? The process of producing flat world ML output. There's this inner loop, right, where you're iterating over what model best fits the data, and you're trying lots of things, and you're going back, and you're retraining and all that stuff. But to do production machine learning well, you also need to add this outer loop, which is the loop that you take your model that's deployed in production, you look at all the data that's coming through it, and you iterate on the data set that's being used to train the model. And so what this adds to the process is once you have a trained model, you need to test it, right? You need to make sure that it performs well across all of the slices of data that you care about, all of the metrics that you care about. Once you've tested it, you need to deploy it. You need to monitor that deployed model to make sure that performance doesn't degrade, which machine learning models tend to do in production. And then you need to collect the data back that's coming through that model and relabel it and then use that to kick off a new training process, right? And so one way to think about like what this, in an ideal world, what this allows you to achieve is you're building a data flywheel, right? And the concept of a data flywheel is that you want to have a system where as you make your model better, that actually makes your product better. As your product gets better, you get more users or more information from your users. And that extra data allows you to produce a better model, which then closes the loop and makes the product better, right? And so this is like the data, like this sort of process is what enables you to have a data flywheel, which I think is like the key to building successful machine learning models that you can maintain and improve over time. Okay, so this is the transition that machine learning teams need to make right now, and I think it's kind of I think the stakes are pretty high. So I'm going to claim that machine learning teams that don't make this transition are not going to be around in like 5 or 10 years. Couple of pieces of evidence that I'll point to. So two sort of very hypey machine learning companies, Uber's ATG division and Element AI, which was a kind of a research lab, consulting lab founded by a bunch of very famous machine learning researchers in Montreal, both recently sold for less than their previous valuations. And I think in Element's case, it was actually less than the total funding that they had raised. So like pretty bad outcomes from the market there. On the flip side, if you look at kind of maybe what I would argue is like the biggest beneficiary of the AI hype era, which is OpenAI. OpenAI is actually going through a pivot right now, right? Like they're pretty squarely focused on commercial products these days. And in fact, like a lot of their sort of core research focused people recently left to start a new company. So OpenAI sees the writing on the wall here. And just, one more piece of evidence I'll share just as a way of thinking like what impact this will have on, the rest of the world outside of like buzzy AI startups. Kind of interesting survey data here, right? So I think the takeaways here are that like the majority of executives from the survey say that like machine learning is taking more time than they estimated. There very, very few of them are actually using the stuff in the real world. And kind of crazy statistic, 20% admitted on the survey that the only reason they did this to begin with was because of peer pressure and hype. Right. So imagine what's going to happen to these companies like when the hype bubble from the leading edge starts to wear off. But I don't want to paint a negative picture here, like because I actually think the upside of this transition is much more exciting. Well, actually, before I get to that, first of all, like, what does this mean for you as like someone who's working in data, working in machine learning, right? So one implication of this is, I think, over the past like 5 years or so, there's been this like, what I think will look back as an anomaly in history, where people who are really good at training complex models, that's like the like the highest paid and most prestigious job in the data world right now. These like ML researchers, right? I think that's going to be that's going to catch up with us really quickly. And then the other implication I think is relevant to you all is that the outputs of sort of old world machine learning teams, right? Papers, dashboards, proofs of concept, I think looking forward are not going to be enough to make your team successful. But the upside of all this is that I think that teams that are able to like make this transition and start building machine learning enabled products and services instead of reports are going to create like really amazing things over the next 10 or 20 years, right? And so when people think about like implications of machine learning, I think a lot of focus is on sort of like the big ticket items, right? The autonomous vehicles, the real-time translation systems, the drug discovery systems, right? And I think those things will generate a ton of value for the world. But I think what's really underrated is the long tail of applications of machine learning, right? So the process of machine learning becoming embedded in like almost every product and service that companies offer. So it's things like marketing automation and personalization and document understanding and things that are like not necessarily sexy to the New York Times, but are actually going to generate a massive amount of value as they get rolled out at scale. So this is the opportunity, right? Like this is the stuff that we'll create if we bridge the gap. But it's challenging, right? So there's some pretty big differences between machine learning products and sort of these flat Earth machine learning systems. And to categorize a few of them, right? So not all machine learning products have all of these, but these are some common challenging aspects. So unlike sort of traditional machine learning papers, machine learning products often run online and they run in real time or near real time. In academic ML, you have sort of a fixed data set and you're iterating on that data set. The data set never changes. In the real world, the data that you're trying to make predictions on is shifting over time. And in the real world, like data is not as clean as it is in academia. It's messy, right? It has long tails and like features that you don't really know how to capture. And then I think one other difference is that in the sort of analytics or like report producing kind of paradigm of machine learning, there's a pretty slow loop between predictions that a model makes and changes that a business makes, right? Because you're incorporating those predictions as part of a decision-making process. On the other hand, a lot of machine learning enabled products are going to be required to make predictions autonomously, right? Like make recommendations to users autonomously, or decide what's in a document autonomously, or if not autonomously, in many cases semi-autonomously. So as part of a tighter decision-making loop that say a customer service rep is doing. And so the challenges that these present are, I think that there's some pretty big ones for infrastructure and tooling in the machine learning world. So for one thing, right, if models are going to run online, we need to be able to host and serve models with low latency. If data distributions are constantly training, that means that we need to be able to detect when they change, and we need to be able to retrain models frequently, or even in some cases continuously. If data is long tail and it's messy, we need to have really good tools for kind of scalably inspecting your data and managing like slices of data that we care about and edge cases that have hurt your model in the past. And then if our models are going to make decisions relatively autonomously, we need to like be able to really quickly catch and diagnose bugs and distribution changes, because otherwise those, there's not a human in the loop that's going to be helping us make up for as many of the errors that models have. Okay, so this is kind of this is my view of like where the machine learning field is going. So the next thing I want to talk about is like what's going on with the like tooling and infrastructure world. Like how is it keeping up with this? So going back to this loop, like let's focus on the parts of the loop that are relevant to this like kind of data flywheel effect, right? So there's a lot of tools that are aimed at helping make the training process easier, right? So there's tools that are that help make training more efficient or more scalable or easier to do. So there's training infrastructure tools. As you scale out your machine learning efforts, you're running more and more experiments, and so keeping track of those experiments becomes challenging. So a category of experiment management tools has emerged. And then in this kind of machine learning product world, since you have to retrain the models pretty frequently, since data distribution changes, being able to reproduce training that you did before is especially important, right? And so there's a bunch of tools that are emerging also around making pipelines, like training pipelines, reproducible. So I actually think this category is like pretty well served. Like I think the tools that are emerging for training models are starting to get really good. Okay, let's look at testing. Here, I think there's a little bit less, right? So if you think about what you need to do to test a machine learning model, what you're really trying to do is you're trying to like build a very granular understanding of the performance characteristics of that model, ideally in an automated way. So there are some tools out there for kind of manually inspecting the performance of the model. So, weights and biases has some features for this, and there's the what if tool from Google. But this doesn't really tell you like what you should be looking for, and it doesn't really like point you in the right direction of like indicating that there might be a performance issue in your model. So there's another category of explainability tools, which are aimed at like helping humans understand the performance characteristics of models. And then there's the nuts and bolts of like how to run all of these tests. And so there's an older category of CI/CD tools, which is like reasonably well suited to ML use cases, but not perfect. So here I think there's like actually some big gaps. There's a couple of things that are still really, really hard to do when you're deciding whether to put a model into production. One is like how do you surface what parts of your data the model's not performing well on, right? Like how do you know if there's like this one category of users where like, even though your model is performing better on every other category, it's performing so much worse on this category that, you shouldn't put the model into production. And then, even if you do have those test cases, right, those like slices where you particularly care about performance, managing those slices, like keeping track of them, the infrastructure for making sure that you have consistent versions of them across your team and you're running your models on them is still hard. All right, so deployment, right? Like turning a model into like let's say a web endpoint. There's a bunch of tools that have emerged for model serving. And there's another category called feature stores. And for those of you that are not familiar with feature stores, the like one sentence version of what is a feature store is a feature store is like a database that makes the stuff in the database available in a consistent way, also online, like for low latency requests. And so feature stores are about like making the features that you create available for your model in real time. They do other things too, but that's the quick version. But again, I think there's some things that that are still hard for a lot of teams to do here, right? So one thing that's hard is experimentation, right? So like once you've tested your model, you want to still look at its performance characteristics in production by running an A/B test or a shadow test. There's not really great tools for doing that yet. And then keeping models consistent between the version that you trained on and then the version that's actually deployed causes a lot of bugs in production ML systems. All right, moving on to monitoring. So a couple categories of tools that help with monitoring ML models. One is data quality or data drift tools. All right, so you have DQ and TensorFlow Extended are tools from Amazon and Google respectively. And then Great Expectations is a data quality tool. I think many of you will be familiar with. That is kind of an independent player in the space. There's also system monitoring tools, right? So Datadog and CloudWatch and New Relic can help tell if your model is actually up and serving predictions, but they can't really tell you like whether the predictions are accurate and whether the data that's coming through the models are of high quality. But maybe using these two things together is a good starting point for model monitoring. But there's some gaps here too. So one thing that I don't really see out there is performance monitoring, right? So ideally, what you want to keep track of the ground truth performance of your model in production, which in many cases is very difficult. But there's proxies that you can use, like how your users interact with those models, or like you can label a subset of the data. But connecting that back to understanding of model performance, I think, is still missing. And then, although these tools do help you assess data drift, I think data drift is kind of a moving target. Detecting drift, particularly like in high dimensional data, like images or text, is not a very well understood problem, and I don't think the tools address it very well. So moving, back up the loop. So collecting, what data do you want to collect? How do you store the data that's going through your models? I think the data lake and data warehouse sort of field helps with this, but there's some hard problems, like not specific to machine learning, but that come up a lot in machine learning. One is, how do you decide what data you're going to store, right? So in a lot of machine learning use cases, you can't actually send all of the data back to your servers. So which data should you send back? And then another thing that I think is missing from like kind of generic data lake and data warehouse is connecting the data that you're storing back to the model, right? So for each data point in your data lake, which model made the prediction on that data, what was its prediction, how accurate was that prediction, so that you can start to like use that data to make decisions about retraining. So there's data labeling tools, which I think most of you will be familiar with. And there's a new category of tools that are aiming to help with data labeling, which I would call like active learning tools. And so these are aimed at like helping you, they're mostly focused on computer vision right now. They're aimed at helping you like navigate your data set and find interesting parts of the data manifold to send off to your labelers. But there's still some big hard problems here too. Deciding what data you should label, right? Like labeling data is expensive. So how do you get the most bang for your buck? And then related but slightly different question, deciding which of your data should you actually train the next version of your model on to get the maximum performance. I think these are pretty unsolved problems. Then lastly, to close the loop back to training, there's still a question here that is plaguing a lot of teams, which is, how do I even know when I'm supposed to retrain my model, right? Like retraining is expensive. So should I retrain like every hour, every day? How do I know? Like what's a good way of deciding that? And then I think another one I'll put in here is retraining online, which is kind of a big focus for a lot of companies now. But I would say the training part of this is not really the hard part. The hard part is like understanding how well you're performing in production well enough to know that your retrained model is actually better. Okay, that was kind of like a whirlwind tour through the production machine learning infrastructure landscape as it relates to building machine learning products via data flywheels. So what should we take away from this? One thing is that, I guess like one kind of obvious thing is that there's just a lot there, right? There's a lot of tools that are emerging to address some of these problems. So that's like both good and bad, right? There's a lot of people trying to solve stuff, but too many tools is often like worse than no tools at all. And a lot of the problems that you see, I think, are kind of arising at the boundaries of these tools, right? So how do you get data from your production system back into your data warehouse in a way that it like maintains the integrity of like the quality of the predictions the model is making? And I think this is especially true for any part of the system that involves like shepherding a data point through this process, right? So from the time that it's created, when like a user sends you a request, all the way back through like when you retrain the model. The path that an individual data point takes through that process is still like not very well captured. And then another thing I'll point out is that one common thing that we saw across many of these stages is that one thing that's lacking is getting a really good kind of granular understanding of model performance, right? So, and this is true at the testing stage. It's true at the deployment stage when you're running like an A/B test, and it's also true at the monitoring stage. And so the next thing I want to talk about is I'm going to propose an idea that I think might help address a lot of these challenges. And so this idea is the idea of the evaluation store. And so the way I would define an evaluation store is it's a central place to store and query both online and offline ground truth metrics and approximate metrics for model quality. So I'll explain a little bit more what that means. So how to think about evaluation store. Okay, so like one way to think about evaluation, like any kind of system component, is like, what are the inputs and outputs? So what goes into an evaluation store? So one thing that goes in is like the feature values and the predictions that the model is making, both in training and evaluation. Another thing that goes in is the labels. A slightly tougher to understand thing that goes in is user-defined data slices, right? And so the way I would think about this is like, you want to have some way of providing to the system, like telling the system what subsets of the data you care about breaking out performance on. Other thing that goes into the system is feature values and predictions from production, right? So we're linking training and production here. And then the last component is any feedback that you have on those predictions, right? So those could be labels. In many machine learning use cases, labels are hard to come by or expensive. They could also be business metrics that are correlated with the model outcome. They could also be, the feedback that your user provides you, right? Like, did the user click on this thing or not? So those are the inputs to the evaluation store. What are the outputs? Well, one is, the reason why it's called the evaluation store is model evaluation metrics, right? So accuracy, whatever metrics you care about assessing the performance of your model on. And you want those on like all of the models, like all the models that have ever gone into production, and on your offline data, right? So on the data that you are training and validating your model on, the data that's labeled, where you can actually get good estimates of these metrics. For online data, what you want is approximate performance metrics. So I'll talk in a little bit more detail about what I mean by this, but you can think of this as like things that would allow you to guess whether you think the model should be performing well on this data that's seeing production, right? So it's things like, is this data drifted? Or is this data point an outlier? Then I think the other thing that comes out is a mapping of performance metrics to data points, right? So you want to be able to see like, okay, give me all the data points where my model performed the worst, or where I'm the least certain about how it performed. And you want to be able to do stuff with those. And then you want to be able to look at diffs, right? So for different versions of models, how do these evaluation metrics, both ground truth and approximate, compare? And how do they compare not only in aggregate, but also across all the slices that I defined? Okay, I'll make this a little bit more concrete in one slide, but first I'm gonna go on a little digression about what I mean when I say approximate performance metrics, right? So again, like place you where we are in the life cycle here. Approximate performance metrics are, in production, in a perfect world, when a new data point comes through our system, we would know right away how well that model performs on that data point and every other data point in production. In the real world, it's often really difficult to get a good estimate of ground truth performance, right? So labels can be unreliable. They're often really expensive. And in many ML use cases, like probably most ML use cases, if you get labels at all, they come at a massive delay, right? So this doesn't help you if you need to know now how well your model is performing. So approximate performance metrics, like I would define this as ways to guess which data points that are coming through your model might have poor performance. So some examples, right? When people do drift detection, right? In the context of machine learning, right? So looking at the distribution distance between inputs that we're seeing at training time and inputs that are seen in production. Why are we doing this? Well, one reason that we're doing this is because we want to get some estimate of like whether we think we should still trust the model's performance, right? So distribution distance drift is an approximate performance metric. Outlier detection is also an approximate performance metric. Our model might not perform well in outliers. If you're familiar with the snorkel stuff, then like slicing functions, or like which is basically like the stuff that the functions that your experts are creating. Those are an example of approximate performance metrics. If you're not familiar with snorkel, don't worry about this one. but check out Snarkle, it's pretty cool. And then, another category of things here is like metrics about your users, right? So like maybe user engagement might be an approximate performance metric, right? That doesn't tell you actually how well your model is performing, but could be a proxy. Okay, so let's make this a little bit more concrete and talk about how this fits into your like production machine learning system, right? So I think the way I would categorize this is like, I think the evaluation store should kind of sit in the middle of this outer loop and help shepherd data and models through the loop. So let's talk about how it interacts with the different steps, the different components of the system. So for training, when you train a model, you're going to want to register the data distribution that the model was trained on and the performance that the model had in training into the evaluation store. So you can use those to compare future versions of the model. But the evaluation store should also be an input to your training process, right? Because one really common source of bugs in machine learning is, you change the way you compute some feature. It's no longer consistent between training and production. You train model on bad data, you get a bad model, right? So evaluation store should also warn us if training data doesn't look like production data. All right, so let's talk about testing. When you test a model, what you're doing is you're basically running that model on a bunch of historical data, and you're comparing a bunch of historical data that you have labels for, so you can get ground truth estimates of performance. And so your testing system should register that performance on all the slices of data that you've defined that you care about back into the evaluation store, so you can compare online performance with offline performance. But the testing system should also read from the evaluation store, right? Because when a data point comes through the system that had bad performance for an old production model, or very uncertain performance from an old production model, right? Like an outlier data point, or a data point where a human has said like, yeah, the model didn't produce a good prediction on this data point. Those are the exact kinds of data points that you want to feed back into your testing system. So the evaluation store should also be keeping track of all the data points that human says or automated system says are interesting to test on. So how does the evaluation store interact with the deployment system? Well, the deployment system, the production data coming through the deployed model needs to go back into the evaluation store somehow, as well as the performance, or the approximate performance. But you also might want to use the evaluation store to as part of your deployment process, right? So if your evaluation store can tell you approximately how well are all of the versions of the model that I have in production doing, then the evaluation store is exactly what you should be using to perform an A/B test, for example. So how does the evaluation store interact with monitoring, right? So evaluation store can tell you how well do I think my model is performing over the last 5 minutes, let's say. So that's, monitoring is a pretty simple extension of that, right? You just fire alerts whenever the approximate performance on any of the slices that you care about dips below some threshold that you define. Evaluation store also interacts with data collection, right? So one way to think about this is if you're deciding what data to log back to your system, well, you might want to just take a uniform sample of that data, but you might want to upsample parts of the data where your approximate performance is low, or where the approximate performance is uncertain, because those might be interesting data points to retrain the model on. In the cleaning and labeling process, a similar phenomenon happens, right? You might want to inspect and label data that the evaluation system flagged. And then finally, when it's time to retrain, the evaluation store can tell you when to retrain, because really the way that you should decide when to retrain is a sort of cost-benefit analysis, right? Where you have approximation of how well your model is performing. That tells you, and hopefully you have some idea of how much a different performance affects the business metrics that you're trying to drive. And so if that is below the cost of retraining the model, or above the cost of retraining the model, then you should retrain your model. Okay, one thing, maybe for those of you that are very familiar with the MLOps world might be thinking is hang on a second, shouldn't this just be part of the feature store? So I think there's some pretty critical differences here, right? So feature store is indexed by feature, evaluation store is indexed by model, right? So that's a critical difference. So if a model is like taking a feature as input, that doesn't mean that it takes every single data point that has that feature as input. So the distribution that a model sees might be different than the distribution a feature store sees. And a poor quality feature, so a feature that's drifted, has different impact on different models, right? So for one model, it might be a really important feature. For another model, it might be a very unimportant feature. And then, not all data is really going to come through the feature store. So I think it doesn't make sense for this system to live in the feature store, but these two should absolutely talk to each other. Joe, how are we doing on time?
I got as much time as you need. Go for it.
Cool. I just have a couple more slides. So another like reaction you might have is like, wait a minute, isn't this just like machine learning monitoring by a different name? So there's a couple answers to that. One is, yeah, yep, that's exactly what this is, right? So the missing link here is approximating how well your model might be performing right now to the best of your ability. And that's machine learning monitoring. That's the goal of your machine learning monitoring system, is to give you your best guess as to how well your model is performing right now. But I would also say no. So some differences, right? When you think of monitoring, you think of an online system. I think it's important for the evaluation system the evaluation store to provide a consistent view between online and offline. Let's learn from the history of ML infrastructure here, right? Like this is a consistent problem across the ML world when things are not the same between online and offline. And I think there's a lot of pieces here that like definitions of slices, particular data points that are interesting, where you want to make sure that you have consistency between online and offline world. When you think of a monitoring system, you kind of think of like the system that's sort of sitting off on its own, watching the rest of your system. But evaluation store is actually very tightly integrated into the rest of the ML ops stack. So I think monitoring is maybe not the right analogy here. And then when you think of a monitoring system, you generally think of a system where it's looking at metrics and it's trying to like flag a problem for you. But evaluation store, it's really important to keep track of what data caused which questionable performance. And the reason for that is because that data is literally the code that you're going to use to produce the next version of the model. So you need to tie your real-time performance back to the data, the individual data points that cause those degradations in performance, or those guesses at degradation in performance. Okay, so this is not an idea in a vacuum. I'll point to like 3 case studies, I think, of systems that have this flavor. I won't go into details because of time, but you can. I recommend checking these out. So one is the Tesla data engine. So Andre Karpathy has a great talk on this. They have a system where their cars are collecting data, but they can't collect all of the data. So when they see something anomalous in the car, like user takes over control from the car, then that inaccuracy is reported back to their system, and then they do this process that they call boosting, which is basically they deploy another model that is used to detect similar examples to the inaccuracy. Then they label that and feed it back into the training system. So the Tesla data engine, I think, is pretty similar to what I'm discussing here. TFX data validation is one of the like open source things that has a lot of similar concepts. The thing I like about it is that they have a link between model performance estimates in training and validation and online. I think they're missing other ways of assessing model performance, like feedback from users. And I don't think they have a very good link between model performance and data points. But I think this is a good step in the direction of what I'm talking about here. And then lastly, this is kind of like an under the radar paper, but I think it's one of my favorite ML infrastructure papers, is the Overton system from Apple. And the Overton system, I think, does a very good job of building a system like what I'm describing here. Okay, so just to like recap where we are here. So I think in order to turn machine learning into a product engineering discipline, we need to build an infrastructure stack that helps us create a data flywheel. Right? So it helps us build better and better data sets over time that allow us to create better and better models over time. So what's still missing? A couple categories of things here. One is sort of granular, offline, online, consistent understanding of model performance. And then kind of orchestrating the life cycle of an individual data point as it flows through that entire loop from, being collected in production to, being logged to being part of a training loop to being part of a test. And the question I pose here is like, maybe this concept can help. Like maybe an evaluation store could help address some of the problems in the MLOps landscape. Great, that's all I have.
Awesome. Hey, thanks, Josh. That was fantastic.
Thanks. Yeah, I'm happy to answer any questions that people have.
Thanks. Hey, Josh. This is Dylan. Thanks for your presentation. Where do we come down on build versus buy for something like this? Are we still building solutions?
Yeah. I don't think, I'm kind of like proposing an idea here. I think some of these systems like have a lot of the same elements that I'm proposing. I think Tesla's system is like a pretty close match. I think Overton is this is only one part of the Overton system, but I think Overton system has this. I think TFX is maybe the closest thing that's available to this. But I think, if you want to create something like this right now, the only choice is build.
And when we're storing data, do we store like the idea of storing references to the data? Do you store all of the data that you use to train? Like,
I think it depends a little bit on your use case. Like I think I imagine that this system, for most users, like the evaluation store itself is only storing like pointers to the data. Because I think for most, in most cases, you already have like a data warehouse or a data lake set up somewhere where like the raw data is going to live. So we don't want to necessarily duplicate that. We just want to we want to know how to map from like anomalies and low performance and low approximate performance back to like which data points cause those things. So you want to know how to like find the data. But we don't necessarily need to keep it here.
But and those so models that will have some pre-processing or featureization, those should be probably stored back to the warehouse and then referenced in the evaluation store. So they're not part of the train. Like, should we be working to separate out our pre-processing from our evaluation?
So what would the argument be for separating pre-processing and evaluation?
Well, so that you could have references to the original data points, I guess.
I see. Yeah. So I think like you want to try to build a system where you have as much lineage for data as possible. So yeah, I mean, in a perfect world, you log like every single, step in the pre-processing pipeline. In reality, you probably have to make approximations to that.
Hey, Josh, I have a question. To kind of back up in your talk, I mean, you talked about how the world is sort of moving beyond training models to, I guess, everything else in this continuum. For people who are just, they're moving away from like flat earth machine learning, as you put it. I absolutely love that term, by the way, it's hilarious. But for people moving away from flat earth machine learning into kind of what you're proposing, where would be, I guess, the most impactful area for somebody to check out next?
Yeah, I mean, I think the first step is building good data infrastructure. So like making sure that you have access to the data that's going through your models, starting to build some lineage into it, making sure that you can reuse that data for training. I think feature stores are maybe a reasonable starting point. I haven't actually evaluated any of the feature store offerings, so I won't make any recommendations there, but they might be able to do some of the stuff out of the box.
Sure. And feature stores are an interesting one too. It seems like even the people making feature stores are still trying to figure out what a feature store is. So some of the talks we've had with some feature store folks, but yeah, I mean, it's pretty fascinating seeing this, I guess, because as you pointed out, for the longest time, everyone was very focused on training models. And yet there's like this entire universe, I guess almost a separate universe outside of that. So So it's a lot.
When we're implementing things like this, there's an approach that a lot of the vendors are taking where it's essentially putting this infrastructure around notebook code. Is that something that you still do, or does everything go into like modules and into a package for the code? Like how should we be structuring projects around this?
Yeah, it's a good question. I don't really like believe in this idea that we're just going to build better tools around notebooks and then notebooks are just going to become production systems. Like I think there's some problems with notebooks that are like pretty fundamental to notebooks as a format. Like, how do you know what state a notebook is in? That make them like really bad candidate for production systems. Mm-hmm. So hopefully there's like a way of bridging that gap a little bit where like, maybe, I don't know, maybe you can translate from a notebook to like more traditional code setup. But yeah, I know a lot of people are like trying to build systems where you can just like take your notebook and turn it into a production model. But I think it's like, you're always going to have bugs. It's like going to be really hard to avoid that.
And then hard to evaluate where those bugs are. Yeah.
Hey, Josh, thank you for the talk. This was fascinating stuff. On the side, I write a newsletter on MLOps. So I'm waiting for the day when there's more information about the evaluation store on the internet, so we can cover that. But I had a quick question in the meantime. Mm-hmm. So for small companies, startups with very small ML teams,
yeah,
in what order should they kind of build out the different parts of this evaluation store?
It's a good question. I think so. The very if you think about like the process that you go through as as you mature as a machine learning team, right? Like first thing you need to do is figure out what problems to work on. Then you need to find some data, make a proof of concept, like demonstrate that you can actually solve problems using that data. And then the next thing you need to do is like figure out how to actually deploy that model. So the first thing that you really need to think about is model deployment. And there's some pretty simple ways of doing that. And then there's also some very complicated ways of doing that if you have a complicated system. Once you've deployed a model, the next thing I would make sure that you do is get the data that's coming through that model logged back somewhere. So build a simple data lake, right? So you just have a record of what's going through the model. And you can start to use that for like training future versions of the model. And then I think like one thing that is massively underrated in the machine learning world right now is monitoring, right? And so that's the next thing I'd put in place is like just put some really simple checks around that, around the data that's going through the model, because it's like so common for model performance to degrade in production. And every company like starts out thinking like, oh, that's like, we'll figure that out later. It's not a big problem for us. And then you hear these like horror stories of, massive outages that end up costing millions of dollars because who knew that model was actually really valuable. So that's the third thing I would think about.
Cool. Thanks.
A question for you, Josh, and maybe for anyone else. So, while you're talking about this flywheel process, you've listed out all those tools to do all this different stuff. And, I think it's a pretty common process where everyone vets out these tools and tries to implement a lot of these tools that you find in your flywheel just to create this whole process. And then you're proposing this idea of an evaluation store on top of that. So one of the things that I was noticing is that if you were to create an evaluation store, it seems like it'd be a lot of work to be able to, point to all your different services, all your different tooling, being able to holistically get that. Does it just feel too fragmented in terms of a whole holistic ecosystem? Because you have so many tools for all these different jobs. And then if you're trying to get something to, work with all of them together that can, point to everything and not have to store all the data from each of the pieces and recreate them essentially. Like that just seems like a really, I don't know. It seems like it's adding a lot more complexity, although albeit, needed complexity, but it seems like there's always just more and more tooling that we add and it keeps getting more and more complicated.
Yeah, I hear you. I think that like proliferation of tooling in this space is kind of crazy. And And yeah, I think so. Couple things I would point out there. One, like all the tools in the stack need to be connected, right? Like if you want to build working production machine learning systems, there's no way around needing to have the life cycle of a data point from ingestion in the model through like how good is my model's performance on this data point to like storing that data point somewhere to deciding to labeling it to deciding to retrain on it to retraining on it to like putting it in a test case somewhere. Like that's an unavoidable part of the process. And I think so like how can we do that without a ton of complexity? So one alternative solution is like everyone should just buy end-to-end machine learning platforms, right? But I actually like really hate that idea because I just don't like using tools like that. It's terrible. Like you're not building the exact same machine learning models that like every other team is building. You're building models that are different. They're like suited to your use case and your data looks different and you're choosing different architectures. And so like the one size all fits all thing, like it just doesn't really work for teams that like care about building really good models, in my opinion. And but we're kind of left with this question of like, are things just going to keep getting more and more fragmented? I think we'll see some consolidation, and I actually think that like if someone were to do a really good job of implementing this concept, then this would actually really help simplify things because this system could basically be your monitoring system and your testing system, and it could help connect the like sort of missing pieces between the rest of the systems, right? So it could talk to the feature store, it could talk to the training system, and it could make sure that like things are consistent between them. I think that like it's much better to have like a tool like this that sits in the middle and eliminates some pieces than to like be trying to build all those connections yourself. So yeah, that's my view. I think that like I think some of the tooling categories are going to consolidate, but yeah, like I think even if it's complicated to integrate with a system that connects everything together, it's better than like building a system that integrates everything together.
Yeah, and I guess I would add on to that. It seems like anybody who does try to do the one size fits all solution ends up failing in some respects because, like you said, it's pretty hard to generalize so far. And honestly, a lot of the ones I have seen seem to do just the flat earth one size fits all and not the whole cycle.
Yeah. I'm bullish on end-to-end machine learning systems, but only ones that are focused on very specific use cases. Like, I think you could build a really good like end-to-end image classification system, right? Like only works for image classification, but it like does a really, really good job of putting all the pieces that you need for that together. I'm not sure there's like a market for tools like that, but I think you could build really good tools for that type of thing.
I was thinking it would be nice to have some sort of framework, like web frameworks, like the way that Django has sort of opinions and a structure for like, here's how we design a web backend. If there was something similar where, there's different pieces like, oh, we want to use a different database backend and we want to use different middleware, layers, different authentication. Yeah. Like you can swap out pieces, but having some sort of framework for ML would be nice.
Yeah, like a canonical stack. I think that's a matter of time. Like I think people are building tools in all these categories right now. It's all a jumbled mess. It's unclear how they all fit together. But it's in everyone's best interest to have an ecosystem of like tools that work well together. Because for all of the like machine learning tooling and infrastructure companies, the main thing that's holding them back is just like how quickly this market is going to grow. And so if there's like a really cohesive system that you could put together by, just saying like mix and match between tools A, B, C, and D, and then like if you don't like D, then you can build your own thing, or you could swap that out. Or if like C doesn't fit your use case, then there's also E. Like that level of like building blocks, I think is like what's everyone's incentives are aligned to create that. So I hope that's what's going to happen.
Do you think Kubeflow is furthest along on that sort of like whole ecosystem, or?
Probably, yeah.
So basically we'd need to agree on like a common set of interfaces or something, kind of like the common container API that, you know, connects Docker and the other solutions that are supported by Kubernetes. Does that sound right?
I think that's one piece of it. But it's also about like, it's not just enough for the tools to speak the same language. Like, I think the integrations need to be a little bit tighter than that. Yeah.
Hey Josh, I have a question. So do you see this closed loop coming like an adaptive system where like you use reinforcement to change itself, or is it more like we see a trigger and then we change something in the model?
I think that like there's very few examples of companies using reinforcement learning right now. So I don't think so in some sense, like, I don't know, because I'm not sure what it would take to, you know, even though I like worked in a machine learning or like a reinforcement learning lab for my PhD, and like I care a lot about productionizing machine learning, I still don't really feel like I have a good sense of what it would take to actually put a reinforcement learning system in production, because it's just so complex. But I think that I think it's sort of a walk before you can run scenario, right? Like, I think if you build a system like what I described, where you have a really tight loop between like model performance and retraining, where you can like detect, you know, reasonably quickly that like, it looks like things are degrading, so we should retrain, and you can shepherd that model through the process. Then it feels like you have a lot of the building blocks that you need to put a reinforcement learning system into production. Probably not all of them, but at least it's like some scaffolding for that.
So when do we start applying machine learning to the machine learning engineering?
It's already happening. Yeah. No, like, all joking aside, people are doing this.
Yeah.
It's auto ML.
Yep.
Josh, I had one question. Yeah, I work in a deep learning environment for a healthcare company. And I see most of the things in our process the way we do it. We add one extra step in, you know, when we get data from the field, we actually run that data through a model, through one of our models initially to pre-annotate, and then we select the low confidence values of that data to focus on. The high confidence data is good, but the low confidence data is the stuff that's our kind of pre-filter.
Yeah, that's great.
Yeah.
Oh, sorry. Was there a question?
No, it was just a statement. I didn't know if that's done in the field.
That's awesome. I think yeah, it's a really simple thing. More people should be doing it.
Yeah. And then for the validation part, we have a gold set of data, a gold set of validation data that's been peer reviewed. It's like our test plan. And so we have, say, 50,000 images that have been peer reviewed and are valid. And we run our models on that test set, and then run all the map numbers, and all of that stuff gets stored in a database. That's basically how we do it.
Do you, are there particular edge cases or like slices of that data where, like, is it just a single metric or like a single set of metrics that need to pass? Or is it like, you know, accuracy has to be this high on all the data, but it also has to be this high on like all of the data for this particular feature value greater than this thing?
Yes, we have, say, 14 things that we're looking for, and we set the map number threshold for that. And then as we get new data coming in that we don't have samples for, then that gets added to the validation set, and we just run that the validation set, and it can rip through these at 1,000 frames per second, and we get those numbers very quickly. And then all of those numbers get posted to a database, and we have a dashboard that shows where we're at. So yeah.
Yeah, that makes sense. Seems like you have a version of this already.
Yeah. And then one final question. Data drift, can you explain that just a little bit more? I guess for imaging, you have possibility where images or different imaging characteristics are slightly different. But what's the concept of data drift?
Yeah, so the idea of data drift, or like maybe the more like inclusive term is like concept drift. And the idea is that like when you train a machine learning model on a data set, right? So input, let's say it's a supervised learning model, input and output pairs. Then there's an implicit contract that you're making that the data that you look at in production is going to come from the same distribution as the data that the model was trained on. In the real world, there's all kinds of things that can violate that that assumption. So data drift is like when the distribution of inputs to the model changes. And so things that could cause that. So your user's behavior could change, for example, but other things can cause that, like bugs, right? So let's say that you have a bug in the pre-processing pipeline that you deployed, and it changes how you how you normalize your images, right? So before they're between, like you in training, they're between 0 and 1. In production, they're between negative 0.5 and 0.5. That'll tank your model performance, right? So that's another example of data drift. Yeah. Does that answer the question?
Yeah, it does.
So Josh, when we talk about data drift and approximate performance, it kind of feels like you're looking for something you don't know. Like you don't know what you don't know, but you know it somewhere could be a problem. Is there a more definitive way to say this is where it is, or we just know it's a problem that could arise somewhere?
I don't think that there's a definitive way of answering this question, right? Because like if you could say for sure what the performance of the model was without labeling it, then you'd have a perfect model, right? You just ask that. You'd ask that thing what the performance is. So all of these, like all of the ways of doing this are heuristics, basically. And so one of those heuristics is like, we know that if the data coming into the model looks really different than what it was trained on, it probably is not performing well. Especially if the data from features that are important in the model's decision making are really different, right? And so you can start to drill down with heuristics like that. Or another example is like, in the Tesla data engine thing, right? Like one thing that they do is when they have an anomaly, right? When they have a event where a user intervenes, then an engineer will go and they'll build a small model that's designed to detect similar events to that event. And they'll deploy that on the car alongside the production model. And they'll use that model to flag like, noisily flag similar data to the original data point that came in. The reason and the rationale there is that like user is like the ML engineer is saying that like data that this model says looks like this anomalous data point is more likely to be bad, model performance. So yeah, it's like a bag of heuristics, I would say.
Does it make sense to what kind of database or data structure goes into this like evaluation store? Is it a relational database? Does it have like what's the structure of the pieces? You have like a model ID because of what you had was like this is essentially at the model level, not at the feature level. So you have a model, and then you have what else?
Yeah, I mean, I think I don't really want to like get too much into the details because I haven't not prepared to talk about that yet. But yeah, I mean, there are a lot of moving pieces to track, so it's like not a trivial problem.
Mm-hmm.
Any other questions?
Cool. Well, thanks everyone. It's really great to be here, and Yeah, again, working on a startup now. We haven't talked publicly about what we're doing yet, but if you're interested in like the idea of what it would take to build something like this, then we should chat. This is kind of one of the ideas that I've been thinking a lot about recently.
Awesome. Yeah, thanks. I think this has been one of the better discussions we've had in a long time. So it's obvious you've thought a lot about this problem. So
I don't only think about this problem these days.
Can't tell. So yeah, it's awesome. Cool. Well, thanks, Josh. And I guess if somebody wanted to get a hold of you, what's the best way for them to find out more about you?
Yeah, should I just drop my email in the chat? Is that the easiest thing?